Hello. This is not really a lab submission. It's just I it's the last day to get work in, and I'm a little bit shot from another exam I had that took a lot of time, and so I just thought I'd get the Adafruit out and try to figure out how some of it works. So up there I have a low frequency oscillator, and it's varying between like 1 and 5 volts, and so I have it coming out of channel A, and there it's going into the power rail. I thought it would be fun to have a switch to turn it on and off, but I didn't realize this is an inverted switch, so it only turns the circuit off if you push it down. So I was trying to play around with the resistors, but I don't remember the ratings anymore. So this red one, I think, is it's of a much higher resistance than this one, but you can see it should dim significantly if I pull the red one out. Kind of, yeah, that's dimmer. So I don't remember the exact mathematical expression for it, but basically just because of the way resistance is calculated with reciprocals over parallel circuits, the more resistors we have in parallel, the more increases the current that's flowing through here, because it actually decreases the resistance. So if we put more resistors in parallel, we get a higher current, and the higher our current, then that's going to go through the LEDs, and the LEDs are, in a way, they're like their own resistor, except that instead of putting off instead of dissipating their energy as heat like these guys, they're going to dissipate it as photons. So it's a photodiode, and then it just comes back out and goes that way. Yeah, and you can obviously increase the frequency of the wave, but it's going a little faster, is it? Let's get it going. Let's try. Huh. That's interesting. So I shrank the period, and I'm not sure the rate of the flashing changed. Maybe I didn't do it enough. Let's try again. I'm doing something differently than before, because before I got them flashing pretty rapidly, but going to expand it out. Oh, that's interesting. Okay. So if you look now, I've got a really huge period, really big wavelength. And it's not that the frequency looks, the frequency of the blinking isn't changing so much as the second order rate of change. Like, there's more of a ramp up. So if I shrink the LFO again, make that higher frequency. Let's see. Whoop, like this guy. Then it just abruptly goes on and off, but at the same rate. So it's like I'm taking somehow. I thought it was going to change the rate of flicker, but instead it's like I'm making the current source discontinuous by shrinking the frequency, which is really interesting. It's like turning into a square wave, kind of. But yeah, the one other thing I wanted to play with was the LEDs here are all in parallel so that they have the same brightness, but I can take them out without breaking the circuit, theoretically, and they should get brighter. Huh. They did not get brighter. Which might mean, what does that mean? God, it just goes to show, no, Kirchhoff's current law, right? So the current coming in is the same, but not through each. Man, no, I mean, it's the same net current, but it's being summed between 2 instead of 3, so shouldn't they be brighter? It should get real bright if I just put the one by itself. That's really interesting. So clearly my intuition for this stuff is not where it should be even after the final, but now I can chain them in series, and here's the behavior where I think I will predict it right, is it should get dimmer if I put them linearly. Let me just make sure I have the power rail. Yeah, so I'm going to have to break the circuit up, and I'm going to start putting them in series one after the other. So make sure the long end is first, because that's the positive wire. And here's another one. Oh no, my dexterity is not as good as it was. When I was a kid, I did a lot with Legos. Gives you good coordination, but I haven't done that in years. There we go. So now we've got them in series. And now let's link the rail back up. And we should get sequentially dimmer LEDs because the voltage will... Oh, is that what's constant with a parallel circuit? The voltage stays constant? The drop across all the LEDs is constant when it's in parallel. No, the drop is constant. It's iteratively dropping when it's in series. It's dropping by a constant rate per component because they're all rated the same. But if I have them in parallel, then the voltage holds constant between every component, which is why they're all the same brightness. So now I might have to redo the... Yeah, let's stick this one here. Oh no. And then this one's gonna go here. Push it in. Oh, no, no, come on. You can do it. Oh no, I did something wrong. What'd I do wrong? Let's find out. So now there's no blinking. Maybe there's not enough. Let's double check. So let's look at the path I'm tracing. So the resistors go here, meets up with the... Oh no, they are on. Look at that. They're on. They are very much on. It's just the camera probably can't pick. If you look at it right from the very top, there's a teeny tiny flash. Right. So something about... God, I'm basically falling back on intuition from high school electrostatics, where they... If you want to step up current, you got to put lots of resistance in parallel, and I'm kind of doing that here. But I think the diodes themselves, their resistance is significant, and so you have to put the diodes in parallel. But that makes me wonder, what happens if I stick a resistor in parallel with a diode? Oh no, shouldn't be doing this with one hand. I think this one will be bright, maybe. So I'm gonna put the negative one there. Here, one sec. Try this again. Oh man, this would be a good time to get the pliers out. see. Okay. There's one. Nope. So, did I break the circuit? Yeah, now it's really broken because this guy's got to go. The rails aren't closed anymore. Here we go. Yay! Look at that. Okay, so now I'm using one diode. This one is functionally just a resistor, but it's adding. These guys in parallel are making a big enough current that these two guys in series are getting enough voltage to be bright. So now if I wanted them to be really bright, I can put them back in parallel, I think. So I would have to take line up the negative. Whoa! Something happened. I just shorted something. What did I do? That's real interesting. Look at that. I wonder what's going on there. I have no idea. So if I put I'm closing it, but I'm putting the negative, I'm connecting it to the negative end of the diode, and that's doing something. Watch this. That's really bright. God. So I'm putting I'm putting the negative end in series with the negative end of this guy, but his positive end isn't going anywhere. Which is really weird because what did I change? So now let's finish it. But we were originally going to put these two in parallel. Like that. There we go. Nicely done. And then we take this guy, we're going to break it. But no, we're not. Oh no! Oh, that's really weird. So it had nothing to do with the fact that we were connecting to the negative terminal, it's just because he was broken. Because before this guy and the guy I'm holding were in series. And when they were in series, there was a big voltage drop. So this guy didn't have a lot of, I guess, potential to draw on for making light. And similarly, it knocked this down. But now why are these two of equal brightness? That's really strange, because these guys are not in parallel. Unless, are they? Node to node. No, they're in series. So as a last thing, what I wanted to do was get you, where's the negative end? Like that. Whoa, are they all the same brightness? Huh. Funky. What is the... I'm doing some kind of square wave here. You can see I'm making a current. Let's compress it a little bit. Wait, no, isn't period the reciprocal of frequency? Yeah, because 2 equals 1 over f. So I think actually this really slow frequency means we have a really fast period. Or I wish, this is all stuff. So I'm 23. a lot of this I did when I was 15, so it's been a long time. And most of what I did with the course, the textbook material, you don't develop intuition for this. You do the computational circuit analysis, but it doesn't really hammer home how a lot of this works. So it's a little sad I'm only playing with this now at the end of the semester because, yeah, it's fun. But let's just watch what happens if I... Oh, okay. So see that generated current? So me varying the voltage source... Oh, that's also part of it, because I'm on an AC circuit. Well, what happens if I go very dim? Okay. Come on, you can do it. Where is it? No, I wanna... Oh, there we go. Okay. Yeah. Quite bright. That is interesting. It's still pulsing. Why are you still pulsing? So the current being measured is steadily at like 0.1 amperes or something like that, or milliamps. A whole amp would be pretty dangerous. So I have you hooked into channel A. Wow, okay. I am way over my head here. Well, my intuition about upping voltage to get bigger current to make more light dissipation was correct, but that has nothing to do with what happens if I take you out. Way dimmer. So this diode is highly resistive compared to these two teeny tiny things. I don't remember the color code. But it still doesn't tell me why this is fluctuating, because if you look, the current line is flat and the voltage line is flat. So where's the periodic behavior coming from? What if I take out... Nope. Okay. Well, there's one other thing I can do. Signal is coming from channel A. If I want to guarantee that it's constant, I can stick it into the 2.5 volt port. Yeah, okay, so it's something in the way I configured LT-Spice. Not LT-Spice, whatever this is, the pixel pulse. Yeah, so 2.5 volts supplied. It's quite steady. Let's make it bright by adding our resistor up, maybe. Interesting. Interesting. Yeah. Well, what I learned here is I have no idea what I'm doing. I do have my... I guess one last thing we could do is measure... Let's see. Do I want to measure? Let's measure current. So I'm gonna hook it over to that, and let's try some milliamps. So 0. I'm gonna measure the current at each terminal of the diode. So let's grab, oh no. Let's see how this works. I don't think I can do it with one hand. Okay, you're gonna have to take my word for it. Red goes to positive. Black goes to negative. That's interesting. It doesn't really want to stabilize. So for me, when I just put these on, it's fluctuating between like 0.1 and 0.5 milliamps. So maybe it's because I'm not steady with my hands and I don't know what it is. I really don't know what it is. I wish I had paid better attention during lecture, but that still gives us a range, though, to give us a sense of if these guys, when the voltage source is DC, stays like this, then what I'm curious about is let's stick it back into the oscillating channel. And for whatever reason, the root mean squared current seems to be a lot larger. So here we go. Channel. Hey, can I hold it? Yeah, let's hold it. Oh yeah. Here we go. But now this guy's totally dark. I wonder if I killed it. Certainly possible. Just a moment. Or maybe I had the orientation. It is a diode. It's a one-way diode. Well, all diodes are one-way. I don't know. Let's just stick this guy back in. Good enough. Maybe I did kill it. I'm not sure. I've got my blinking guys, and now I'm gonna take the current, milliamps again. And I don't know how lumens correspond to amperes, but we'll find out. Oh yeah, wow, that's like a factor of 5 more. So it jumped up to like 1 whole milliamp, up from like 0.2. What's interesting about that is got my channel A voltage, stair step. Let's just play sawtooth. Nope. Huh. Well, okay, sine. Oh, look at that. Very tiny. What I don't like about this program is it's hard to drag stuff. Like I want to increase this value here and I can't figure it out. There we go. Okay. There we go. Now I'm gonna get that frequency to change. Was I doing a sweep before? What was I doing? Constant. Triangle. Yep, and that's very jarring. Can we do stair step? I'm not sure there's a change habit. I'm changing the I'm changing the oscillation type, but if I set it back to constant, interesting. I don't know. Anyway, this is running too long. You probably don't have 25 minutes, but I just wanted to show that like I do enjoy this. I don't understand it, but I do enjoy it. And thank you for this semester. Bye.